everyone, and welcome to ATARC's Quantum Speaker Series. I'm Elizabeth Wyckoff, ATARC's Working Group Program Manager, joined by our Working Group Chairs, Allison Schwartz, Lily Chen, and Terrell Franz. Today, we are very excited to welcome our speaker, Professor Jacob Scheffer. Professor Scheffer's research focuses on computer architecture and hardware security. His research encompasses secure processor architectures, cloud security, FPGA attacks and defenses, hardware FPGA implementation of cryptographic algorithms, and most recently, quantum computer cybersecurity. He is currently an associate professor of electrical engineering at Yale University, where he leads the Computer Architecture and Security Laboratory. If there's time at the end, we will take questions, so please feel free to add them to the Q&A. And with that, Jacob, please take it away.
Okay, perfect. Thank you, Elizabeth, for the introduction, and thanks for the Advanced Technology Academic Research Center for the chance to give this talk. And like Elizabeth mentioned, I'll watch my timer, and hopefully there is a little bit time at the end to answer some questions. But if not, feel free to email me at any time, and I'll try to kind of connect by email. But anyway, today I'm going to talk about design of secure quantum computers. So this is our research that's looking at how we can help make quantum computers secure by first looking at potential vulnerabilities in the quantum computer systems, and then proposing some defense. And our research, like a lot of quantum computing research, is motivated by the sort of rapid advancement and development of quantum computers. So as you're probably familiar, around 2000, we had machines with few qubits. In recent years, there are 50 qubit machine from IBM, 72 qubit from Google, 128 qubit machine from Rigetti, and constantly there are new machines put online or announced. So, for example, in November, IBM presented the 433 qubit machine, and then IBM has projections for 4,000 qubit machines in a year or two, and other companies like Rigetti are also projecting rapid growth. And actually, just last month there was an announcement that IBM is targeting 100,000 qubit quantum-centric supercomputer by 2033. So there's a lot of investment in these machines, and in some way, maybe it's kind of similar to the early years of the Moore's law, where we have rapid development in number of Moore's law was transistors, but here qubits and capabilities of these systems. And so the quantum computers promise that there will be new developments and new results that they can generate in chemistry, materials research, or medicine. And today, these machines are sort of, we call it the noisy intermediate scale quantum era, where we have less than or around 100 qubits and some moderate error rates. But in parallel, there's also already a lot of research on fault-tolerant computers. So hopefully, in the future, we'll have large quantum computers, fault-tolerant computers that can run different algorithms to, for example, find new drugs. But the question we're trying to answer and trying to kind of promote other people to kind of think about is, are the quantum computers secure? So once we have these quantum computers which can develop for example, new chemicals or new materials, unfortunately, there'll probably be some malicious users that are trying to affect the operation of the quantum computers, or possibly steal the information. For example, find out what the new medicines or new materials are. So we want to kind of find out, are the quantum computers secure, and how could we make them more secure by design from the bottom up? And then, so in this first part, I want to talk about some possible quantum computer vulnerabilities. So these are not any specific security attacks against quantum computers, but more of different types of categories of possible vulnerabilities that our group has been researching, and some other groups have also started to look at. The idea is to try to think about how could somebody attack a quantum computer, and then once we know that, then we can design defenses. And fortunately, still the quantum computers are being developed. So if we can propose the defenses early on, hopefully they can be incorporated. So by the time we have this 100,000 qubit machine, not only is it very capable in terms of computation, but it's also secure. So one way to think about possible quantum computer vulnerabilities is to look at a typical quantum computer system and see which parts could be potentially attacked. So this is an image courtesy of IBM showing a setup for a sort of a typical superconducting qubit machine. So in the three parts would be sort of the laptop representing the classical digital computer that sort of sends commands to the quantum computer. Then in the middle, we have the different RF electronics, arbitrary waveform generators. So this is the equipment that basically turns the commands into the RF pulses that are sent to the actual quantum computer. And on the right side, this is sort of a diagram of the inside of the fridge that holds the actual cube. And nowadays, also in addition to these parts, these are not standalone computers, but they're actually cloud-based. So maybe you're already familiar that IBM Quantum, Microsoft Azure, or Amazon Bracket are some companies that are providing cloud-based access to small but real quantum computers. So sort of anybody with a credit card can access these computers and kind of try to run some very simple circuit. And then, as the machines get bigger and bigger, of course, types of quantum circuits you can run are getting bigger and bigger. And a lot of the companies, for example, IBM and Amazon and Microsoft are sort of also offering, sort of some free access for researchers, but also pay as you go access to general public. So that's kind of their, it's like any cloud-based computing setting, you can pay to use these machines. And so, unfortunately, once these machines are sort of accessible by sort of arbitrary users, different parts might be vulnerable to security attacks. So the three parts that could possibly be vulnerable. So on one hand, we could have software vulnerabilities in the control software. Then there could be some vulnerabilities in the controller electronics. So actually these, classical computers, we already know quite a bit about security, but for example, not many people have researched security of, arbitrary waveform generators or, for example, FPGAs that are used in generating these control signals. So there could be security issues with the controllers. And finally, of course, the new part are the qubits and the quantum operations that are happening on them. So there could be security issues and vulnerabilities within the qubit. So these are sort of the three parts that we sort of should think about when we're trying to design a secure quantum computer system. Now, in terms of where the potential attackers could come from, there's sort of two main types, we believe. So first of all, there are the remote attackers. So any random person with a credit card could go to one of these companies and submit jobs to be run on the quantum computer. So then this is one type of so this could be a malicious users that we should be able to protect against. On the other hand, there are also possible local or physical attacks. So in classical security, there's sort of a well-known notion of an insider threat or an insider attacker. So for example, even if you trust IBM, Microsoft, or Amazon to kind of be honest and not try to steal any information, there could be malicious insiders, engineers, or somebody who has physical access to these machines that could actually be probing them. And unlike classical computers, tiny chips made of billions of transistors, so far quantum computers are sort of room-sized machines that might be much easier to physically access and probe. So given the sort of the two types of attackers and three types of possible vulnerability points, we can think of sort of remote attacks on the software controller and the qubits, or we can also think about local or physical attacks on the software, the controller, and the qubit. So now to give you a very brief idea of potential vulnerabilities, and again, these are not specific attacks, but sort of ideas we are researching and prototyping. So for example, when we think about remote attackers who submit some malicious jobs to a quantum computer, then we could have, for example, what we call a circuit virus attack. So the idea is that, for example, we have two users running on the same quantum computer. So this is an idea of multi-tenancy that some other researchers have proposed a few years ago, that if you have a huge quantum computer, you can share it among many users. So then, like on a classical computer, you have different circuits running in parallel. And so one malicious circuit could generate, for example, some crosstalk that actually affects the victim circuit, in this case, the Grover's 2 qubit. And until we have fault-tolerant quantum computers with error correction, actually the crosstalk could affect the computation results. So a circuit virus could try to affect the results of another circuit. On the other hand, the crosstalk is bidirectional. So we could also think of a situation where there's a circuit that's running on 2 qubits, and then the different gates that are executing as part of that circuit generate different amounts of crosstalk. So a malicious circuit or a malicious spy could actually be a circuit that tries to detect the amount of crosstalk and then use that to detect what operations the other user is performing. So this crosstalk could be used for like a circuit spy attack. Now, considering the software, the remote users, but they're also the physical attacks. So one of the key problems or challenges that the quantum programs kind of contain all the intellectual property and all the data of the circuit. So until we have quantum random access memory or quantum databases, you sort of encode all the data and the operations into the quantum program. So if somebody is able to steal your quantum program, then basically they find your intellectual property. So given a physical or local attacker, for example, somebody might be able to leak the programs from the memory of the management system. So this is pretty much a classical computer security problem, but still, if they're able to extract the program from the memory, then they could get, for example, the input values or your proprietary circuit. So I'll mention at the end, there's some existing solutions like Intel SGX that might be able to protect from such program leaks from the memory. But for other types of attacks, more on the quantum, on the qubits and the controllers, we're proposing some other defense. Now moving on to the middle part, we can think about the controller. So again, the controller could be exposed to either remote attacks or local attacks. So the controllers are basically used to generate the control pulses. So in terms of superconducting qubit machines, they use RF pulses, where you have an arbitrary waveform generator that generates the control pulses for each type of gate that you're trying to execute. And then that signal is mixed together with some carrier frequency, and those are the actual pulses that are sent to the quantum computer. So you might have an arbitrary waveform generator in a separate mixer, or now recently there's some FPGA-based setups that might be able to actually generate directly all the necessary signals. But in the end, there is some waveform generator that generates the pulses. And the pulses can be predefined for fixed gates, but also you can have custom gates or custom pulses. So to kind of allow for research on different types of operations or different types of circuits, a lot of the quantum computer providers and backends support custom pulses. Now with custom pulses, there is a danger that somebody could define a pulse that exceeds the specification of the equipment, or send some unusual pulse sequence or shapes of pulses that are not supported by the equipment or weren't really considered or tested. And this way you could actually maybe create some damage or have a denial of service where you sort of crash the waveform generator or all the logic. So this would be one way for a remote attacker to try to, for example, damage the remote equipment, or at least create a denial of service. With some, so you have a malicious, for example, pulse sequence that's sent to the waveform generator as part of a circuit that you're trying to execute. On the other hand, you could also have some physical or local attacks on the controller. So again, so far quantum computers are sort of room-sized equipment that might be easier to probe, especially the controller electronics are outside of the cryogenic fridge, so it might be literally be able to connect cables to probe what's going on. And like I mentioned, we could have a cloud provider, which we assume might be honest, but there could be malicious insiders inside the data center hosting the quantum computer. So one possible type of sort of attack that leverages physical proximity or physical access to a machine could be a power side channel attack. So in a power side channel attack, you can think of basically an attacker connecting power traces from the waveform generators, and then from the power traces, they could try to reconstruct some or all of the gates that are being executed on the quantum computer. And then once they can reconstruct the control pulses and the gates, they basically can reconstruct the parts or whole of the circuit that's being executed. So even if the sort of all the all data is encrypted being sent to the cloud provider, even if the cloud provider doesn't try to access the data, at some point the quantum circuits are transformed into the control pulses, which are sent are generated from the waveform generators and are sent on the RF cables to the quantum computer. And then so this is the point of vulnerability where somebody could, for example, launch such a power side channel attack. And I should also mention that in addition to power side channels, you can have EM side channels, where you look at electromagnetic radiation, although the cabling used in quantum computers is pretty well insulated. So so EM attacks might be less possible, but still we know from classical computers that there's a lot of research on EM attacks on classical computers, and somebody can probably find a way to do it on quantum computers. And again, they're not going to be getting the you can't get the state of the qubits or any information from the qubits themselves, but if you can get the information about the control pulses, then you can basically reconstruct the program. And then until we have something like quantum random access memory or quantum databases, all the inputs are encoded into the program itself, so you can get not just the program but also the input data to that program. And for example, as some of just to give some nice graph of some our recent research, for example, we've looked at using the different side channels for user circuit identification. So, for example, if we take a set of all of the QASM benchmark, which is the quantum assembly benchmark developed by a different research group, basically we can look at measuring the duration or the timing, which is the red line, or the mean power or the total energy, or looking at the power time series of the circuit, and then you can see that we have very high accuracy, almost 100% for small number of possible layouts, where we can actually identify the circuit purely based on the timing or the mean power or energy. So this is actually a very basic attack that can be performed, and you could recover which circuit from among the benchmarks that the user is executing. And then there's some other types of attacks that we're exploring in our research and in the publication. For example, we can look at the circuit oracle or ansatz identification. So again, if you can identify the control pulses, then you could try to identify basically the type of ansatz or the type of oracle that's being used by the quantum computer, and then also by the quantum circuit, and then also qubit mapping. So so today at least different qubits have a slightly different amplitudes and for the control pulses. So for example, if you can capture the details of the control pulses, you could figure out how the qubits are being mapped to the how the qubits from the program are being mapped to the physical qubit. And then sort of the ultimate goal for a potential attacker would be to reconstruct the whole user circuit from the power traces. So this way, somebody might be able to get information about the proprietary circuit that the users are executing. So next, or the third part are actual qubits where the computation is happening. And then so again, there could be some potential remote or local physical attacks on the qubit. So on the remote end, we kind of been looking at how a users could try to learn some information based just on the outcome of their operation. And one of the things that people have looked at is physical noise, or like I mentioned, crosstalk earlier in the presentation. But they're also the operations themselves can be imperfect, and imperfect operations within the quantum computer could end up leading to some information leaks. And then so one type of operation that we've been looking at is the reset. So reset is the operation available from or a gate available from IBM. I understand Rigetti is also supporting the reset operation. And then so in order to basically isolate different shots of circuits or different circuits themselves, you have to reset the qubit. And normally you would let the qubits thermalize or decay, but that sort of the longer you have the decoherence time, then the longer you have to wait to let the qubits decay. So if you just let the qubits sort of naturally decay, it perfectly erases the state of the qubits, but then it takes 250 or probably longer microseconds as the decoherence times increase. So an alternative that's been developed are these reset gates, which basically measure the state of the qubit, and then post measurement, if you're in the 1-ket state, then you apply an X gate to reset the qubit. So it's a really clever idea to speed up the reset of the qubits, but it could be, if the reset is not perfect, it could lead to some potential information leaks between the different shots of a circuit, or maybe even between the users. And so just to clarify today, as far as I know, that cloud-based quantum computer providers are using thermalizing the qubits, so they're using just long delays to make sure the qubits decay between the users and between the shots. So there's no issue. But if they switch to using the reset gate, which is already available, then you could have these different information. And on one hand, if the reset before the user runs is not perfect, then there could be incorrect state at the beginning, which could affect the computation. Or if after the user circuit finishes, if the reset again is not perfect, you could leak some information. And actually, what we've been researching a little bit is looking at the reset gate information leaks, and kind of trying to figure out if a user performs some computation, then you apply a number of resets, and then could the attacker basically measure the qubit and still get some information. And I don't have time to go into the details, but in short, because the reset gate is imperfect, actually the attacker has a pretty high chance to guess whether prior to the reset the state of the qubit is either 0 or 1. So we're not guessing any arbitrary state, but just the 0 or 1 state, which would be the typical state of the qubit after the measurement. So in effect, if this works, you could possibly try to leak the final computation results of the prior user's circuit. So that's on the sort of on the software side, or so where the software attacker simply has this measurement attacker circuit that is executed after the victim circuit. On the physical attack side, on the qubits, there's been some research, especially by Professor Swami Tanu, whom we're collaborating with, at sort of an active attacker that could potentially use EM source to try to inject some signals or modify the control signals. So, for example, by being able to shift the frequency by a few megahertz, actually that significantly cuts down on the fidelity of the different gates, such as the X gate. So a physical attacker who can inject some EM signals into the quantum computer or into the controllers could possibly degrade or maybe even deny service. So this is another type of a threat. So to kind of summarize the different ideas, we can think of this vulnerability matrix where we have two types of potential attackers, either remote users or maybe malicious insider who have physical access, and then they could be targeting either the software, the controller, or the qubit. So on the software side, malicious users could try to use circuits that kind of spy on another user, or just try to disrupt the operation of the other user by leveraging crosstalk, which hopefully would be eliminated once you have fault tolerant and error corrected machines. Considering just the classical controller, there could be leaks from the memory that could be used to steal the circuits if you can access the memory of the classical controller computer. If you think about the RF electronics, remote attackers could try to generate control sequences that basically get them waveform generators out of proper operations, or a physical attacker could measure some quantities such as power consumption to perform a power side channel attacks. And targeting the qubits in the end, we could, for example, try to abuse some imperfect operation of the gates for information leak, such as the reset gate, or we could try to degrade the fidelity of the gates by injecting some EM signals. So now, just to kind of come to the defense part, in a very few minutes, I want to talk about some defenses. First, without trusted hardware. So, for example, if we consider the different side channel attacks, we can have the energy, the mean power, or the duration. So on these graphs, the blue bars are sort of the original circuits. These are the quantum assembly benchmark circuits, and you can see that they consume different energy, different amounts of mean power and duration. So by measuring these quantities, the attacker could simply identify the circuit. So some simple solution, for example, for energy, we could add pairs of X gates. So pairs of X gates rotate the qubits by 2 pi and are eventually an identity. So you could add some X gates to basically make the energy consumption of the benchmark constant, so the attacker can't identify the circuit. For the mean power, you could add some delay to lower the mean power. So again, they can't identify the circuit. Or for duration or time, again, you can add delays to make things the constant time. So of course, this could be quite wasteful, and currently you might trigger some issues with decoherence. So we have to think of better ways, but these are already simple things we could apply. And then I want of our defenses present in our work on the power side channel attacks. For example, if somebody can measure per channel information from the waveform generators, they could really reconstruct all the non-virtual gates that are executed. So one idea actually left from our prior research on FPGA security is to add some power waster circuits. So if the waveform generators could be basically set to consume a constant amount of power for regardless of the operation that they're or regardless of the pulses they're generating, then that could mask the information from the attacker. So the idea is that before the defense, the attacker might be able to see different control pulses, and then after adding some circuits that cause the waveform generators to sort of consume constant power, the attacker no longer can distinguish if the power consumption is from the actual control pulses or from the dummy power that is being consumed by this equipment. And then also, I don't think I have time to go into details here, but there are certain gates such as RZ gates, which are called virtual gates, and they don't actually result in any control pulses being sent to the quantum computer. So you can basically try to decompose your circuit into different circuits that leverage more RZ gates, which might not be possible to be captured by the attacker. And again, I can see our work on exploration of quantum computer power side channels to get some more details. And then just very quickly talking about some defenses with trusted hardware. One idea we're working on is a trusted execution environment for quantum computer. And the idea here is that the digital control signals between the controller and the control computer and electronics could be encrypted. So that's not an issue, but the RF pulses cannot be encrypted. And like I mentioned earlier, we could basically add some pulses, but maybe it's not most efficient. So what we're trying to look at is how to design this trusted execution environment to protect from side channels and to hide the real control pulses. And then very briefly, one idea here is that you have an input circuit that's provided by the user, and so you want to protect the intellectual property of this circuit. So what you want to do is you want to add some decoy control pulses, so the attacker who's measuring some information about the execution cannot find out which are the real pulses and which are the decoy pulses. But then, of course, before the circuit actually gets executed, you have to have some way of attenuating the decoy pulses so they don't actually cause any effect on the qubits. And then to realize this, we have research proposing the trusted execution environment for quantum computers, where effectively you can provide the input program with the decoy pulses that can be all generated by the users. You can provide an encrypted bitmap specifying which pulses to attenuate, and additional logic in the fridge to attenuate the pulses that are not needed. And sort of the details I can share offline, but the idea is that the actual, only the attacker might see all the decoy pulses, but the actual qubits are never affected by these pulses. And so kind of just to wrap up, maybe I see there's some questions, so maybe I can answer them. So towards designing the defense of quantum computers, for the defenses, we can have an antivirus type software for the remote software attacks. Actually, we have some research on this if anybody's interested. For the physical attacks on the software, we can use trusted execution environment, for example, Intel SGX, which is already commercially available. For the controller electronics, we can make sure to validate the control pulses considering remote attacks, or for the physical local attacks, we need to think about, adding decoy pulses or having these constant time or constant energy circuits. So by measuring some properties of the controllers, people cannot guess what are the control circuits, or what are the quantum circuits executing on the machine. And then for the qubits and gates, I can think about design of secure resets. And then for the physical attacks, for example, shielding from malicious RF radiation. So just to summarize, I think that sort of the next frontier of computer security is quantum computer security. There's rapid development in getting the qubits to be more have a better fidelity, have bigger machines, but we also need to design some properties, protections for security attacks. And this is just some of our recent work. But in general, I think our goal and everybody's goal should be to kind of make sure we can protect the computation that's on the quantum computers from the different attacks. So thank you so much. for listening. Sorry if I spoke very quickly, and I think maybe Elizabeth can tell us if there's some time for answering the questions, and if not, feel free to email the questions at jakub.scheffer@yale.edu.
Yes,
And so
unfortunately,
thank
we
you so
don't
much.
have. Thank you so much, Jacob. Unfortunately, we don't have time for questions today, but please feel free to reach out to Chris or myself, and we would be happy to connect you with Jacob. So, Jacob, thank you again, and thank you everyone for joining us. Have a great day.
Great, great. Thank you so much.